Welcome to another Aspire demonstration movie. In this one, we'll demonstrate offline code guards, a protection developed at Ghent University. The security requirement that we want to meet is code integrity. Concretely, we want to protect against static and dynamic tampering with the code. Static tampering, for example, include attackers that use binary editors to tamper with the code in a static binary or library. Dynamic tampering, for example, can happen with a debugger. We want to prevent that people change the code while it is being executed with a debugger. In this way, we prevent true tampering, but there are also other uses of debuggers that we can prevent here. For example, software breakpoints. If debuggers use that, behind the hood, they replace instructions by breakpoint instructions, and so we also want to detect those changes. The way we want to do it is we want to compute hashes on code and then trigger a reaction if the hashes are wrong, meaning that someone has changed the code that we hashed. Now it's important in this context that the reaction is delayed to some extent. For example, we do not want a program to halt immediately after a hash has been computed and has found to be incorrect. Because if we immediately halt the execution, this gives way too much information for an attacker that maybe will want to undo the protection. So this is what we want to achieve. How do we do that? Well, in this project, we have a reference architecture, and in the reference architecture, we have this kind of subsection and sub-design for integrity checking. And overall, we have different phases. The first thing we need to do is invoke an attestator. In this case, we will compute a hash over a code region. Then somewhere else in the program, at a later point in the execution, we will want to invoke a verifier. This verifier checks that the computed hash value of the attestator was in fact correct and stores the result in some way in the program. At the very end of this chain here, we have a reaction. If the check was negative, we want to react by halting the program, by displaying a message, or maybe just by corrupting memory or going into graceful degradation. Or maybe we will inform a server that tampering was detected. Now the important thing here is to keep these steps 2 and 5 apart in time and in space. So in between we have this what we call in general delay data structures. It's data structures that can store the result of a failed verification or of a successful verification, and that can store it in a way that's not obvious for an attacker. So in general we call this delay data structures, and their goal is to remember the outcome of a check, but in such a way that it cannot easily be detected by an attacker. And so ideally, the functions with which you update the status of those data structures and also the functions with which you query the state have to be non-suspicious functions. So this is a general picture. How did we implement this? Well, to explain that, I'm going to use a legend. In red, I'll show source code transformations. So those are parts of this design that we implemented by rewriting source code based on annotations. Then in green, I'll mark part of the implementation that's just implemented by linking in functionality into the program. And in blue, I'll show the functionality that's added by rewriting code at link time. So that means we're going to rewrite the code, the binary code, with the Diablo link time rewriter that was developed at Ghent University. So first we start with pragmas that mark where attestation should happen. And these pragmas are just replaced by function calls by our source level tools. We also use pragmas to mark where verifier calls should be inserted into the program. Now in our implementation, these verifier calls, they hard code the storage of the outcome. And so in fact, we do not have a separate invocation here, but we just have one invocation of a verifier that immediately updates the data structures that we remember the status of the tampering. Now, the attestator and the verifier, they are just linked into the program. These are predefined functions together with the data where the outcome will be remembered and the code that triggers the reaction. Yeah? So this is all just linked into the program. At that point, no reactions will be triggered yet because this point has not been inserted. The way we do that is with link time rewriting. And actually, in our current implementation, we just insert invocations of reaction functions, and those functions themselves check the status of the data structures to find out whether or not some reaction actually needs to be triggered. So these functions are invoked anyway, and depending on what's stored in these data structures, they execute a real reaction or they just let the program continue execution. Our link time rewriter decides where these invocations are put in the program, and actually they are sprinkled throughout the whole code. And to choose where to sprinkle these invocations, we have 3 priorities. All code in the original application logic that is annotated with pragmas and that is marked as code regions, there we inject lots of invocations because that's the code that embeds all the assets in the program to be protected. Then other code that's not marked, but that's part of the original application, that receives a medium amount of invocations. And then we have archives that are linked into the program, but we assume that the externally linked in code is not that important security-wise, so there we inject much less invocations of the reaction functions. Now, even if we've done all of this, this does not suffice yet to have a good offline code guards. The problem is that these attestators here do not yet know which regions they have to guard, for which code regions they have to compute hashes. Now what we do is in the source code, we mark those regions with pragmas. The annotations are extracted, and then at link time, we inject a description of the regions into the program. And also at link time, when the final protected program has been generated, we compute the expected values and we inject them into the program. So this is done at link time, the description of the regions, that's where all the annotated source code that needs to be guarded, where it ends up in the program. It might be dispersed over the whole binary. And also the expected values for those regions. Those are injected in the program at the very end during the link time rewriting. And then the attestator uses the description of the regions and the verifier uses the expected values to check whether or not the attestations resulted in correct hashes. So at an abstract level, this shows how we implemented offline code guards and how we support them. Now let's look at their deployment in an example program. That program will be bzip, a widely used compression program. So here we see the compressed stream function that we want to protect. We mark it as a guarded region, and as you see, if we scroll down the whole function, you see that the end of the region is at the very end of the function. We also give this function a label, compressed stream loop. Then if we look for this label further down in the program, you see we find another location where we insert a pragma, where we specify that an attestator should be injected. This attestator also gets a label. And then further down in the program, we also specify with the pragma that a verifier should be injected, and we use the same label as before. And you can check that again here. So those are our annotations. Then if we look in the compiled code what it looks like, and we look at the preprocessed bzip file, we see it here. You see that where we had the pragma for the attestator, we now have an actual call and declaration of an attestator function. Also, where we had the pragma of the verifier, you see that such a call has been injected. So that's what we described also with the slides. If we look at some of the code that's going to be compiled and linked into the program, you see here that we have a verifier. The label that we use is part of its name now. You see that this will put in some output. It also performs a check. If the check fails, it will invoke the ruin failed function, and that actually, with a call to a precompiled function, starts the degradation. So it updates the delay data structures to mark that a check failed and hence that tampering was detected. To demonstrate that this protection works, we'll demonstrate it on a real attack. And what we'll do in this case is we'll look at the compressed stream function. It has a function call to this write open function, and depending on the output, it goes to error handling. We will edit this branch such that it continues executing unconditionally and that it never invokes the error handler. So let's have a look here. First, we copy the protected binary to a board. Then on the board, we execute the binary. You see that the attestator prints out some results and also the verifier does that, but the program succeeds correctly. It just ends. And you see that the attestation result was the same value that's used by the verifier, and that was the same as the expected result. So everything is fine. Now we delete the output, and then we're going to try to debug this program. So we're going to start the program. We will inject a breakpoint. Now we have already reverse engineered the binary. We're not going to show this, but we detected the address where we want to change the control flow. So this is the address. We set the breakpoint, and then if we execute the program, the debugger, of course, will inject a software breakpoint at that address, and you see that the attestation failed and it detected the tampering. You see that the hash value is different, and that hence the attestation failed. In this case, the behavior that we triggered as a reaction was double free and the program crashes. If we execute the program outside the debugger, of course, this still succeeds, no problem. Now let's do a static attack. For that, we're going to launch IDA Pro and edit the program. And what we'll do is we'll change the branch if equal by a branch always. So we look, so we open the program, we look up the address that we already know from our reverse engineering effort. Here you see this branch if equal. Now we're going to open the hex viewer. We see the branch here, and we replace the OA, which is the opcode of jump if equal. We're going to replace it by EA, which is the opcode of jump always. Then we apply the changes. We're going to write the changes to disk. Then we close IDA Pro. Then we copy the newly edited file to the board, and if we execute it there, you see that it fails. An attestation result is computed, but when this is checked against the expected result, of course, it's different. In this case, you also see that the hash value is actually different than the hash values computed before, and that's of course because now a different branch was encoded, while the debugger inserted a breakpoint instruction which had a different opcode. So obviously the computed hash also differs. That's it for this demo. Thanks.